Okay, so the problem we're dealing with now is finding areas bounded by graphs of functions. And if we can do that, then given any old shape, if we can define the pieces of that shape, the edges of that shape by the graph of functions, we'll have a technique for finding areas of general objects. So first thing I'll do is define these two functions, give them names. I'll call them f and g so that I won't make any mistakes later, and you can get just a quick refresher if there's any puzzles of how to code this in Mathematica. So notice that I hit enter, not shift enter, but I hit enter just to get a new line in the same cell. When I'm talking about cells right here in that there's a little thingy up there that lets me know that this is an input cell. So let's see, g of x. We use colon equals usually when we're defining a function. And that is x squared minus 2. And then I hit shift enter so that now the kernel, the thinking part, the computational part, not the part that we see, but the behind the scenes part, now has stored in it these current definitions of f and g. And if later I define f and g in another way, I would have to enter that cell. Okay? Okay. Normally, I plot things. So what do I mean by the bounded, what does this mean by the bounded area? Let's find out. So I don't know. I'll go from minus 10 to 10 and then deal with it and see if that's even in the ballpark. Most textbook problems like this have their activity at least somewhere around the origin unless otherwise. I mean, there's no reason why the area couldn't be bounded 10 million to the right of the origin, but normally textbook problems don't work that way. Let's see here what I got. Okay, so there's the parabola, there's the sine that shifted down, and it looks like they're talking about this piece right here, which is between 0 and it looks like 2. So let's take a shot at it, change this from 0 to 2, and see what I get. And notice I'm not specifying a plot range so that I'm letting it decide what the plot range ought to be. Okay, so this shape right here is what I'm going after. Now, when you did your reading, you saw it was a subtraction of the top curve and the bottom curve. And the order in which you subtract makes a difference whether your area will turn out positive or negative. So what do? Well, we've got to find these boundary points here, the x values for these boundary points. So I'm going to solve when they're equal to each other. So when is f of x equal to equals g of x? And I know, look, if I don't put reals here, I know it's going to choke on this. It's like I don't have any way of doing this because when it says solve, without me putting in the domain, it assumes I want all solutions, including all possible complex solutions. And that's a bear. But if I put in reals like that, it does this thing. It says, okay, I'm thinking of one root of this equation. It should be something like this. So it goes ahead and does it numerical and hints at it. So I'm going to put a big N in front of that. Now that's a different command. Nsolve says try to find the roots numerically. Don't try to do it exactly. And it gives me these two. Okay. So if I want to integrate, what do I want to do? I want to integrate f of x minus g of x. Oh, they're having mac and cheese in there, and I am hungry. I will go get some in a second. Bless you! Boom. All right. 2.53471. Okay. Now, the question comes, why does subtraction give us the correct answer? Why would I subtract those? I mean, it makes sense if I say it, but it doesn't mean that mathematically there's any kind of proof for it. So what I want to do is at least take a little bit of time and show you, remind you about integration and how integration is tied to areas. So in the beginning, there was the Riemann sum, and the Riemann sum. Okay, so just to since the picture's sitting here staring us in the face, let me jump in. Here's F, and here was G in this case. And what I've done is I've broken this up into about 15 little sub-intervals and formed rectangles. So the idea of a Riemann sum, this thing right here, was to add up the height and the width of a rectangle. Now you're used to seeing F here, not F minus G, but if you look at it, the height of this rectangle right here, like this red one here, is the height of that is this value minus this value. And because this is a number line, it doesn't matter when it's going down below the axis or above the axis. If you subtract this value, this y value from this y value, you get a positive height there. And then if I multiply by the width, and in this case it would be the interval from here to here divided by, I think, 15 is what I've got, or something like that. Probably something around there, like maybe 17 or something. But that would the width there is my delta x, so it's b minus a over n, however n is. And I'll remind you that that's how we approximated this area, and then we took the limit as n went to infinity, meaning that as delta x goes to 0, that the width of these rectangles gets smaller and smaller. We took the limit as they get skinnier and skinnier, and argued we defined what we meant by the definite integral as this limit. If this thing limited to a value, and we found that if f and g are, that whatever's sitting here is continuous, and the difference of continuous functions is continuous, then whatever's sitting here is continuous, this limit will exist, and that number will be our area. Now, you also did the fundamental theorem of calculus that said to find this actual number, we don't have to take this limit of the sum every time. We can actually take the difference of the antiderivatives of this thing, and that was the big punchline of Calculus 1. So anyway, once you look at the rectangles, you can see that this is the way you want to go as an integral of the difference. And sometimes the functions are defined in terms of y instead of x, and so you're going to want your rectangles going this way, and you're going to have dy instead of dx, and delta y instead of delta x. And some of the problems are like that. So, hope that helps. It's beautiful stuff, and I'll talk to you soon.